Have you wondered how electronics make decisions? How your phone turns your screen on and off, or how the traffic light changes from red to green, or even your computer solves problems? Logic gates. They are the building blocks of digital electronics. They basically receive binary inputs and give out binary outputs. By that, I mean they perceive their inputs as zeros and ones, low and high, which can mean yes or no, true or false, but they do so really fast. And if so many of them are put together, as in processors, they can solve maths and even run programs. Let's note that 0 for Boolean logic is false, and 0 for voltage state is low, and 1 for Boolean logic is true, while the voltage state is high. Some basic logic gates include the AND gate. I've seen this circuit represented as an AND gate at different times. Even if it looks like it should work, it has issues. So whenever the input A is low and the input B is high, that's when you have a 0 signal here and a 1 signal here. Nothing flows through because this transistor is open. There is no current flowing into the base, so you can't have current flowing through from collector to emitter. So you can't have any current flowing through this place. Even if this transistor is activated, you can't still have anything flowing through because there's nothing here. But unfortunately, you're going to have current flowing from your base into the emitter because it's more like a diode sitting there, and the diode is going to be forward biased. So you're going to have current flowing from the base into the emitter, which would flow through whatever it is you placed on your output. And if it's an LED, it will most likely turn it on. So by sending a 1 signal or a high signal to base and a low signal to A, you have your output already high, which isn't what AND gates do. So this circuit is bad for an AND gate. Let me introduce you to this circuit. This is a proper AND gate circuit and will give us exactly what we desire. Okay, so whenever we have a low signal here and a low signal here, automatically this point is going to be high. If you have either of them having a high signal and the other having a low signal, we're still going to automatically have a high signal here. We're going to have a low signal here only when we have both of them high. Once we have both of them high, we'll have a low signal here. And this low signal will give us an inverted output of what we get at this point. So when we have a high signal at this point, we have a low signal on our output. When we have a low signal at this point, we have a high signal on our output. And when we have a high signal at this point, we have a low signal on our output. So we can see from the table that that fulfills the criteria for AND gates. So we see when A has 0 signal and B has 0 signal, our output is 0. When we have 0 at A and 1 at B, our output is 0. When we have 1 at A and 1 at B, our output is 0. But when we have 1 at A and 1 at B, we see we have our output to be 1. Now this is a proper AND gate circuit. So this is the AND gate. Alright, so you can see I press the first button, no response. Second button, no response. But pressing them together, we have our LED turned on. Okay. Next, the OR gate. Okay, so we have 2 transistors again connected together, but this time we connect their collectors together and the emitters together, and we take our output from this point. Okay, and we have A and B for our input. So from the table we can see that whenever we have a low signal at A and a low signal at B, we would have a low signal at our output. If we have a low signal at A, a high signal at B, we'll have a high signal at our output. If we have a high signal at A and a low signal at B, we would have a high signal at our output. If we have a high signal at A and a high signal at B, we would have a high signal at our output. Okay, so we have an OR gate circuit here, and you can see if we press either of the buttons, our LED turns on. Okay, if we press both, we have it on. Okay, so our OR gate triggers if either of the buttons are pressed or both are pressed. Now, simple applications of this can be a trigger circuit for multiple sensors, maybe a proximity sensor and an LDR light sensor. So this circuit will trigger if light is detected or someone approaches. Okay. Another application can be house security, a door sensor, window sensor, to trigger an alarm if a door or window is open. So once either conditions, either the door or the window or both are opened, you would have the trigger occur. Next, we have the NOT gate. Now this is also called the inverter gate because whatever signal you send to its input, it will invert it at the output. So if we look at the tables, we'll see that whenever we have a low signal at the input, we have a high signal at the output. So this is the NOT gate circuit. It's also called the inverter circuit. If we send a high signal to the base, the output goes low. If we make the signal go away, that's sending a low to the base, our output goes high. So you can see it's inverted. Okay, so of course this has very numerous applications, even in security systems too, but even down to computation, down to memory and all that. All those we'll go into in coming videos. Next, we have the NAND gate. Alright, so we have two transistors still, and we take our output from the collector of the first transistor. If we look at the tables, whenever we have a low signal at A and B, we have a high signal at the output, okay, because both transistors are turned off. Whenever we have a low signal at A and a high signal at B, that's one transistor turned on, we have a high signal at the output. When we have a 1 signal on A and a 0 signal at B, we have our output to still be 1 because this one turns on at that point and this one is turned off. And when we have a 1 signal at A and a 1 signal at B, we have our output to be 0. So here we have the NAND gate circuit. Okay, so it's an inverted AND gate. We have our output high. So if we send a high signal to either of the base, it remains high. Our output remains high, except we have both bases high. Once we have that, we see our output goes off. For either, it stays on until we have both. So this is a very important circuit that we could use for a whole lot of things, and in combinations with itself, we could even get them into CPUs, have them solve arithmetic, and we could also use them for security systems, of course. For the NOR gates, if we look at our table, when we have a low signal at A and a low signal at B, we have a 1 signal at our output. And of course, that's because both transistors are turned off, so the voltage at the output, which comes from VCC, remains same. So if we have 0 at 1 and we have 1 at B, our output is pulled down because this transistor turns on and pulls down the voltage at our output down to ground. If we have our input at A to be 1 and input at B to be 0, same thing happens. This transistor turns on and pulls this voltage at output down to ground, and so it turns to 0. When we have both inputs A and B with a 1 signal, then both of them are turned on, and same thing, they will both pull down this voltage down to 0. So we only have a 1 signal here when we have zeros at the base, both of them turned off. So this is the NOR gate circuit. Okay, so it's turned on, our output is high. If we send a high signal to the base, we have it turn off. Okay, if we send through the other base, we have it also turn off. If we have both of them high, both bases high, we have it turn off. Okay, so this is more like the opposite of the NOR gate. Okay, so this one has very significant uses. All right, we could use this for sensor switches with memory. Okay, but we'll have to have more of these gates, like 3 of them, 4 of them joined together. Okay, we could have ROS latches with two of them, okay, coupled together. Next, we have the buffer. If we look at the table, we'll see that when we have an input of 0, the output is 0. When we have an input of 1, the output is 1. So it gives us the same output as our input signal. So the buffer can be used to isolate other gates, or it can be used to strengthen or boost weak signals. So this is the buffer circuit. And like we said, when you give a high to the base, the output turns high. When you send the low to the base, the output turns low. So the buffer circuit level follows the input level. Okay, so this basically, like was said, is used to isolate logic gates. Okay, and they can also be used to switch loads, okay, on or off.